Before you is the Cigar Lake mine. Almost half a kilometer beneath the Earth's surface, miners extract rock in which energy is hidden. Energy capable of supplying electricity to more than 400 homes for an entire year. This is one of the richest uranium deposits on the planet, but it is precisely here that the paradox begins. This incredibly valuable uranium, just lifted from the depths, is absolutely useless for nuclear power. You are looking at nature's cruel joke. In theory, this ore can power whole cities. In practice, it cannot keep even a single light bulb on. And this is the hidden problem that for decades baffled the leading minds of the global nuclear industry. Solving this mystery led to the emergence of some of the most classified and heavily guarded facilities on Earth. Ahead lies the path that turns radioactive rock into nuclear fuel. A path through underground icy fortresses, chemical reactions on the edge of catastrophe, and machines spinning faster than jet engines. This is how enriched uranium is created. But before you learn all the details, I ask you to subscribe to the channel and like this video. I need your support because it is exactly what helps me promote my videos. Thank you very much. And we begin. December, the north of the Canadian province of Saskatchewan. On the surface, the temperature drops to -30 degrees Celsius, but at a depth of 500 meters underground, in water-saturated sandstone, there is a fragment of ore designated U-465. It has lain here for almost 2 billion years, and today its waiting ends. The mine operator has been controlling remote equipment at the Cigar Lake mine for 12 years already. However, even after years, every sharp spike on the radiation sensors gives him a rush of adrenaline. It means only one thing: an enriched uranium vein has been found. What is about to be extracted contains almost 16% uranium, record concentration for the entire planet. For comparison, most mines consider a figure of 2% a success, but this is exactly where the problem lies, one that nearly put a cross on the entire project. The uranium vein lies beneath a layer of sandstone completely saturated with water. Imagine that you are trying to dig a tunnel while above your head a continuous stream of water collapses, comparable to Niagara Falls. Ordinary mining methods simply do not work here. The solution the engineers came to sounds like science fiction. They decided to build an icy fortress underground. About 200 steel pipes, each of which is installed over 8 days, are arranged in a perfect circle around the U-465 deposit. On the surface, a freezing unit is started. A calcium chloride solution is cooled to -30 degrees and pumped through the pipes. The water around the ore turns into solid ice, forming frozen walls capable of holding back millions of liters of groundwater. Only after that does extraction become possible. The operator directs a remotely controlled drilling rig precisely to the location of U-465. The drill bits are covered with buttons made of tungsten carbide, one of the hardest materials on Earth, second in strength only to diamond. Through the camera, the operator watches as a mechanical reamer, resembling a steel octopus with wheeled tentacles, literally gnaws through the rock. It moves slowly but relentlessly toward the target. At 10:47 in the morning, U-465 is freed from its stone trap and falls into the extraction chamber. The operator picks it up with a remote platform, controlling the process from a sealed room at a distance of 50 meters. The radiation level here is so high that it can cause cell damage, so the air in the mine is completely renewed every 20 minutes. U-465 is lifted to the surface through steel shafts. Then it is crushed by hydraulic hammers whose power is enough to crush a car engine. The rock is ground to the state of sand mixed with water, and by noon, what only recently was a solid stone turns into radioactive pulp. This mixture is pumped to the surface and loaded into truck number 47. Ahead is an 80-kilometer path that will change everything. The operator watches as the machine disappears into the snowy wilderness. Over the years, thousands of tons of ore have been extracted here, but every fragment still raises the same question. Where exactly will it end up in the end? For U-465, the journey is only beginning. On the third day, truck number 47 arrives at a uranium processing plant. Behind bulletproof glass in the control room, a safety inspector is already waiting for it. In 15 years of work, So much uranium has passed through his hands that it would have been enough to supply electricity to half of Canada. But he still treats every new batch as a potential threat. Here, a mistake does not mean just a bad day. It means evacuation, contamination zones, and emergency services. Vacuum systems carefully pump the radioactive pulp out of the truck bed while the inspector watches the instrument readings from a distance of 7 meters. The radiation level is normal, we can continue. Now the chemistry begins. A special acid is fed to U-465. It dissolves only uranium, leaving useless minerals untouched. It is like a situation where you need to separate salt from sand. The salt dissolves, the sand remains. Only here, instead of water, acids are used that can eat through steel. Behind the viewing window, the inspector watches as the solution passes through a cascade of purification tanks. With each stage, there are fewer impurities. The color of the liquid changes, from cloudy brown to pure yellow, as if dirt is gradually turning into honey. Then roasting begins. The temperature rises to 1085 degrees Celsius, enough to melt copper. This is the moment after which there is no turning back. The slightest deviation in temperature and millions of dollars can be destroyed in a matter of minutes. The inspector does not take his eyes off the sensors. Too high a temperature, incorrect oxidation. Too low, the process will not be completed. After 4 hours, U-465 comes out of the furnace in the form of a black powder that no longer resembles the rock extracted from the mine only a few days ago. This powder is carefully poured into steel drum number 2847. The container, with a volume of 210 liters, is designed for railway accidents and serious collisions on the highway. It is sealed, warning signs are applied, and it is recorded in the log. Each such drum contains potential energy capable of powering a small city for months. But for now, this potential is still locked. U-465 still contains only 0.7% uranium-235, the only isotope capable of sustaining a nuclear reaction. To work in a reactor, the concentration must be increased to 3 to 5%. The inspector makes another entry in the log. Over 15 years, 12,000 such drums have been sealed here. Sometimes he thinks, perhaps this very uranium will one day power his own home. But first, it has to go through the most dangerous stage of the journey. A driver of hazardous cargo has been transporting uranium for 20 years already. Nevertheless, every trip requires maximum concentration. Drum number 2847 is placed in a specialized trailer, along with 47 more identical containers. Each of them is equipped with GPS sensors and is under the control of the International Atomic Energy Agency. This truck is not ordinary transport. It is more like a mobile storage facility with reinforced steel walls, radiation protection, and a locking system that would drive even professional burglars to despair. The route is classified. Even the driver himself cannot tell his family which roads he will take. They are not afraid of theft. Natural uranium is almost useless. The real fear is an accident capable of scattering radioactive material along the highway. The driver remembers his first trip. Back then, his hands were shaking, and it seemed that every car around was about to crash into him. Now, after 2,000 trips, the main threat is not fear, but habit. That is why dosimeters are checked every hour, and seals at every stop. A route almost 2,000 kilometers long takes 3 days. Stops are allowed only in specially equipped guarded zones. Armed guards stand watch by the truck while the driver sleeps in a protected room. Ordinary truck stops are excluded. Too great a risk. While driving through the Rocky Mountains, the driver sometimes reflects on the nature of his cargo. Each drum behind his back is filled with uranium atoms that were born as a result of a supernova explosion long before the appearance of Earth. These particles traveled through space, became part of the planet, were buried under layers of rock, lay there for billions of years, and now are heading to the place where they are to take on a new form. In essence, he is transporting stardust. On the 13th day, the truck enters the territory of the conversion plant in Port Hope, Ontario. The black powder inside the drum will soon become one of the most aggressive substances known to science. The driver signs the documents and goes home. In a week, he will repeat this route with a new batch, and for U-465, the most critical stage begins. Day 30th. The lead chemist approaches the blast-resistant window, understanding that the next actions will either unlock uranium's potential or turn it into useless waste. In the sealed chamber, drum number 2847 awaits transformation into uranium hexafluoride, a gas so corrosive that it can eat through skin and dissolve bones. The control panels look more like the equipment of a space mission than an industrial installation. One wrong value, and the entire batch will be lost. Pressure rises. Gaseous fluorine, one of the most reactive elements on Earth, is preparing to come into contact with uranium at a temperature of 550 degrees Celsius. The moment of reaction arrives. Behind the viewing window, bright tongues of flame flare up. The temperature rises sharply, the gauge needles go into the red zone. This is not just a technological process. This is an attempt to tame a chemical substance that strives to destroy everything it touches. The entire installation is made of special nickel alloys and aluminum, the only materials capable of withstanding the aggressive nature of uranium hexafluoride. It is precisely this step that is necessary for the next process. Natural uranium consists of approximately 99.3% uranium-238 and only 0.7% uranium-235. It is exactly the latter that can fission and release energy. Everything else is ballast. These two isotopes are practically identical. They cannot be separated with magnets or chemical reactions. The difference between them is only a few units of mass per thousand. It is like trying to tell apart twins who differ in weight by only 3 kilograms out of a ton. The key idea lay in one observation. Uranium hexafluoride is the only uranium compound that, at relatively moderate temperatures, becomes a gas. It is precisely in the gaseous state that physics finally begins to work. Gaseous uranium hexafluoride enters special transport cylinders. These containers resemble giant metal thermoses, created to hold a substance capable of destroying most metals. The chemist understands. The next stage will be the most difficult. The cylinders are prepared for shipment to the uranium enrichment plant. It is there, under conditions of the strictest secrecy, that rotation faster than jet engines will finally release the energy locked in atoms for 2 billion years. The operator of the centrifuge shop arrives at work before dawn. He enters the territory of a strictly classified uranium enrichment plant, an object whose existence officially few know. Behind the walls of this complex is hidden a labyrinth of thousands of centrifuges, enclosed in steel pipes and reinforced protective shells. The control panels look more like pilots' cockpits than elements of industrial equipment. There is no room for mistakes here. Each unit spins at a speed of about 60,000 revolutions per minute, almost twice as fast as the turbines of a jet fighter. At such speeds, even a microscopic difference in mass becomes decisive. Gaseous uranium hexafluoride enters inside the centrifuges. Under the action of centrifugal force, the heavier uranium-238 is pressed against the outer walls, while the lighter uranium-235 concentrates closer to the center. The process is repeated again and again. Chains of centrifuges, arranged in cascades, gradually increase the concentration of the required isotope. Do you remember that very pellet that was mentioned at the beginning? A small ceramic cylinder the size of a fingertip, containing as much energy as a ton of coal. Then it seemed useless, paradoxical, almost absurd. Now this paradox is resolved. Those very 3 neutrons that distinguish uranium-235 from uranium-238 were concentrated. 99.3% of the locked energy finally got an outlet. Nature's cruel joke turned into humanity's greatest energy triumph. The piece of rock that the miners called U-465 no longer exists as stone, powder, or gas. It exists as energy, pure, controlled, powering the world. The destination of this path was never simply a power plant. It was always the moment when the impossible becomes inevitable, when the useless turns into the priceless, when atoms fulfill the ancient promise given even before the appearance of Earth, the promise to one day light up the streets in human cities. Sometimes, the most valuable things look absolutely useless. until we find a way to unlock their hidden potential. The atoms waited for their hour, and now they power the future. See you next time.